Hello and welcome. My name is Keith Barker, and if you're looking for a little more information on OSPF, you've come to the right place. So regarding Open Shortest Path First, OSPF, this routing protocol, let's just take a moment and confirm why the heck we need it. And here's why. These networks, we have the 10.1.0, the 10.2.0, the 10.12.0, and the 10.23.0. Those networks are like streets. Very much like the street that you live on. Your house or apartment or building has an address that's on a street. And devices on the same exact street, for example, all the devices here on 10.1.0, they can communicate with each other, and all the devices over here on the 10.2.0, they can communicate with each other. However, sometimes people need to communicate with devices on a different street or a different network. And here's an example of that. Let's imagine this PC right here is at 10.1.0.100. It's on the 10.1.0 network, and it wants to have network communications with the device that's not on that same local network, the 10.1.0. It could be PC2, it could be somewhere out on the internet. And for this example, let's imagine that PC1 wants to send some data over to PC2 over the network. And vice versa, PC2 also wants to communicate with PC1. So PC2 is going to live on the street 10.2.0, so the first three octets here are going to be 10.2.0, and let's also imagine it's at .100. Sort of like house 100 on street 10.2.0, while PC1 is house number 100 on street 10.1.0. So when PC1 wants to communicate with PC2, because PC1 sees that the destination is on a different street, it's going to use its default gateway. So we can think of the default gateway as the device who's responsible for taking packets and then forwarding them or routing them to their final destination or towards their final destination. So in this topology, PC1 would send the traffic to its default gateway, to R1, and it would have learned about the correct default gateway to use via DHCP. And then R1 should make a forwarding decision over to R2, and then R2 should make a forwarding decision to forward that packet to its final destination here at PC2. And if PC2 is going to respond back to PC1, because PC1, again, is on a different street or a different network, PC2 would use its default gateway, R2 would need to go ahead and forward it over to R1 in this topology, and then R1 would need to forward the packet up to PC1. So this process of moving the packet from one subnet to another is referred to as routing. And in this example, it's using IPv4, so we could call that IP routing, where we take the packet and each device in the path forwards it one step closer to its destination. And that brings us to the benefit of OSPF, because by default, if this PC had a packet going to 10.2.0.100 and it forwards that packet down to its default gateway, the router by itself is going to do this. Huh? I don't know how to get to 10.2.0 because it's not directly connected. See, router 1 here is connected to the 10.1.0 and the 10.12.0, but by default, it has no clue on how to forward in the direction of 10.2.0. And so there's a few options in training this router, and one of them is to use a dynamic routing protocol, and an example of that is OSPF, where we can train the routers to talk with each other and share information so that R1 can figure out and know, oh, if I need to send a packet to 10.2.0, I need to send it over to R2, and vice versa. R2, via OSPF, can learn that if it needs to forward a packet to 10.1.0, that it should forward the packet over to R1, who would then be able to forward it on towards 10.1.0. So OSPF is an example of a dynamic routing protocol that's used between routing devices to share information on how to reach a given destination network. And a routing protocol where we're training the routers on how to forward, not actually forwarding traffic yet, but training them on how to reach the destination networks. That training process is referred to as the control plane. So when I think of the control plane, I think of learning how to do something. In this case, it'd be learning how to route. And then after the routers have learned how to route, then when traffic shows up and they start forwarding customers' traffic through the network, that's referred to as the data plane. So in the world of Cisco, you're very likely to hear those concepts, and that's what they mean. Control plane is training a device, in this case a router, on how to forward, and data plane traffic is actually doing the forwarding of that traffic. So OSPF is a dynamic routing protocol that's used to train the routers on how to forward traffic. And before we start putting in commands to enable these routers to share routing information between them, we should have a game plan. And by leveraging a game plan, we can also take a look at these concepts as they apply to OSPF. So when we enable OSPF on a device, we are going to assign it a process ID. It's just a number. Like on a smartphone, we have apps. So you might have app number 1 and app number 2 and app number 3. Think of a process ID as just an identifier on a local router of that program that's running. In this case, it's OSPF. So a process ID, router 1 could use number 1, and router 2 could use number 1, and router 3 could use number 42, because it doesn't really matter outside that local router. It's just a way for the local router to track that OSPF process locally as it runs that program called OSPF. So for our game plan, here's what I propose we do. Let's use process ID number 1 across the board, although we don't have to make it match. Just for simplicity, we'll use process number 1 for OSPF on router 1, on router 2, and for router 3. Another ID that we need to worry about is the router ID. Now the router ID does have to be unique. So we can't have router 1 saying, hey, my name's John, I'm the John router, and R2 saying, hey, I'm the John router, and router 3 saying, I'm the John router. They need to be unique, and that's what the router ID is all about. So it needs to be unique, and we can't have a duplicate. So we need to plan that out in advance. And the actual router ID, it looks like a 32-bit, I should just say IPv4 address, because that's what it actually looks like. And once again, for that router ID, it has to be unique, meaning R1 cannot use the same router ID as R2, and R2 cannot use the same router ID as R3. So for our game plan for router ID, for router 1, let's use the router ID of 1.1.1.1, and for R2, we'll use the router ID of 2.2.2.2, and any guesses on R3? If you're saying, Keith, is it 3.3.3.3? If that's your guess, you'd be spot on. And the best way to configure the router ID is to configure and say, hey, Mr. R1, this is your router ID, and R2, this is your router ID, and R3, this is your router ID. However, if we don't explicitly configure the router ID, it will choose a router ID, or it'll do its best attempt to do so. And here's the pecking order for that. If we configure a router ID, that's the one it's going to use. However, if we did not configure a router ID manually for the router, it still needs a router ID. So what it's going to do is going to take a look at all of its loopback interfaces, and it's going to look at the IP addresses on those loopback interfaces, and the highest IP address on any loopback interface, it's just going to take that IP address and use it as the router ID for OSPF. So if you don't configure it, you get the highest IP address on any loopback address. And here's what I mean by the highest loopback address. Let's imagine we have loopback 50 and loopback 90. And on loopback 50, we have the IP address of 23.1.2.65. And on loopback 90, we have the IP address of 12.19.18.77. So then the question is, okay, which of these two is the highest IP address? Well, it's not the actual interface number, loopback 50 or loopback 90. It's actually the IP address themselves that we're looking at. So the highest IP address would be this one right here, the 23.1.2.65. So when OSPF comes up, if we have not configured manually a router ID, it's going to use this exact 32-bit address as its router ID. So if that's what you want, fine. Otherwise, go ahead and hard code it. And then the next question that might logically come up is, well, Keith, if we did not configure a router ID and we don't have any loopback interfaces, what's it going to do then? Good question. If there are no loopback interfaces configured when OSPF comes up, then it's just going to take any other interfaces that have IP addresses, and it's going to be the highest IP address on any interface. So an example of that would be right here, over here on R1. Again, presuming we did not configure a router ID manually and it has no loopback interfaces. R1 has an interface on the 10.1.0 network and the 10.12 network. And let's also imagine we're using .1 as the last octet on both of those. In this case, this IP address, 10.12.0.1, would be the highest IP address, and that would become the router ID for R1. And again, that's only if, in order, we don't have a configured router ID and we don't have any loopback interfaces whatsoever with an IP address. All right, so that's the pecking order for choosing a unique router ID. So I'm going to go ahead and remove these options because we're just going to hard code and configure a router ID to tell it exactly what that router ID is going to be. Another element before we start configuring these routers that we need to plan on is what networks are we going to include as part of OSPF. So router 1 is directly connected to the 10.1.0 network and the 10.12 network, and R2 is connected to the 10.2.0 network and the 10.23.0 network. And so our question here is, which of those networks do we want to include as part of this game called OSPF, so we can share that routing information across the board with other devices who are also running OSPF with us. So here's what I propose we do. We want to go ahead and include this network, and that network, and that network, and boom, that network. So that's 1, 2, 3, 4 networks that all happen to begin with 10 dot something. And then in addition with OSPF, we need to specify for those 4 networks which area we want to use. And think of an area like a group of networks that we want to go ahead and include and share. So not only do we want these 4 specific networks, we also want to place them in an area. And the good thing with areas is that we're always going to start with area 0. So sometimes it's written as 0.0.0.0, or sometimes it's written just as area 0, but that's our starting point. And for most small networks, you really don't need more than a single area. So when they talk about single area OSPF, it simply means we're running OSPF and all of our networks are in one single area. So for our demonstration here, we're going to put all of these networks into area 0. And so one of the things that helped me when I was first learning OSPF was to consider the actual network as belonging to the area. So a router could have like 3 or 4 different interfaces, and some of those networks could be in area 0. Other of those interfaces could be in area 1 or area 2 or area 3. So when it comes to areas, just think about the actual networks themselves being associated with the areas as opposed to the entire router itself. And that's a good way to think about it with OSPF. So let's imagine that router 1, for its networks in area 0, we're going to include the 10.1.0 network and the 10.12 network. On R2, we're going to include the 10.12 network and the 10.23 network and also the 10.20 network. And on R3, we're going to tell it to include the 10.23.0 network. So that's our 4 networks that all these routers agree are going to be participating and advertised through OSPF. So regarding a default route, if we need reachability to any of these 4 networks, we really don't need to have a default route because they are going to learn, these 3 routers are going to know either because of directly connected networks or learn via OSPF, they're going to know how to reach 10.1.0, 10.20, 10.12.0, and 10.23.0. However, if this PC tries to go out to the internet out here, any of those networks on the internet, like 23.1.2.0, and the hundreds of thousands of other routes, these routers don't know how to reach it. So it'd be great if R1 had a default route that went that way, and R2 had a default route that went that way. And so what we can do, instead of having to do static default routes on R1 and R2, we can simply train this router here at the edge, R3, to advertise or inject a default route. And I'll write it out like this because that's often how it appears. So effectively, R3 says to the entire OSPF area and all the routers that are participating with networks in that area, hey, if you ever need to forward a packet and you're not sure how to get there, send it my way. So R1 would end up forwarding towards R2, R2 would forward towards R3, and then R3, hopefully, R3 has a default route that it can use to really forward traffic out to the internet, in addition to using NAT and PAT to do address translation as well. So for our game plan, we also want to train R3 to advertise a default route into OSPF. And I'd like to chat with you about one more important aspect before we put in this configuration and verify that it works. And that is the concept of neighbors in OSPF. And if we think about neighbors, think of it like 2 devices that live on the same street. So for example, R1 and R2, they are both connected to the 10.12.0 network. So they're neighbors on that street. Or at least they could be neighbors on that street if they're friendly enough. And R2 and R3 are both on this street, this network called 10.23.0. So they have the potential to become neighbors. And so with OSPF, when we have neighbors, and specifically fully adjacent neighbors, that means they're willing to share information with each other directly. So it's the concept of neighbors in OSPF that allows 2 devices to go ahead and share information with each other. So we would expect that R1 and R2 would become OSPF neighbors, and R2 and R3 would become OSPF neighbors. So for 2 network devices that are both running OSPF, if they want to become neighbors, we have to have a few things in place. And one way that helps me, even as a double CCA, to remember this is this mnemonic called TAN mat. So think of like a doormat or some other mat that's tan in color, and this will help you remember the 6 things that have to line up and match up if we want 2 devices that are both running OSPF to become neighbors. So one of those elements that have to match is the timers. So in OSPF, there's little hello messages that are periodically sent out. And by the default on Ethernet, the hello timers are 10 seconds. So every 10 seconds, each router says, hey, I'm here, and this is me. And if 2 devices want to become neighbors, that is one of these 6 elements that has to match up. So if you leave the defaults on Ethernet, that's going to be perfectly fine. And let's use R1 and R2 as an example here. Another element that they would have to both agree on and be consistent with is the area number. So if R1 believes that the 10.12.0 network is in area 0, and R2 believes that the 10.12.0 network is in area 2 or 3 or some other area different than R1, that's going to cause these 2 routers to not become fully adjacent neighbors. So they won't share information with each other, they won't be friendly, and our OSPF is not going to work as desired. Another thing that they both need to agree on if they're going to be good neighbors is the actual IP network. So if R1 believes, based on its configuration on this interface, that the network is 10.12.0, and R2 on its Gig01 interface believes it's the 10.13 network, which is different right there, if both devices believe it's a different network, that will prevent them from becoming OSPF neighbors. It's sort of like me living on Elm Street and you living on Elm Street, but one of us thinks the street name is different. They have to line up. They both have to agree on what the actual IP network is that they're both directly connected to. So these top ones are the 3 key ones, and these others also have to match, and for troubleshooting, they can also be important to be aware of. The M is for MTU, the maximum transmission unit. If you don't play with or muck with on these devices the MTU, those should match up. But in some cases, based on the platform you're using, if the maximum transmission unit on the interface is different, maybe one has 1504 and the other is 1500, That would cause these two routers to not become fully adjacent neighbors if the MTU isn't the same on both of their interfaces that are both directly connected to that network. So I'll put a little red line there saying that's no go. Another element that has to match for these two devices is the authentication. Now, by default, there is no authentication. They don't have to prove anything to each other. However, if we start changing the authentication and R1 thinks we're supposed to be using MD5 and a password, and R2 believes there should be no authentication, that could cause the neighborship to not form. So they have to agree on that as well. And then finally, we have the network type. So with OSPF on Ethernet, both of these routers by default are going to believe it's an OSPF broadcast network, which implies that as they send their hello messages to the OSPF multicast address, that they can discover and see each other. However, there are other types. And once again, unless we go in and manually change that, they're going to be the same on both sides. But if we start mucking it up and we say, oh, this guy's point to point, and over here, this guy's broadcast from an OSPF perspective, that could cause the neighborship to fail. So TAN, MAT, all of that needs to be in line and agreed upon if we want these routers to become OSPF neighbors. All right, so let me go ahead and clean that up a little bit. Also, I've got many videos here on YouTube regarding OSPF. So if you go to my channel and you just search for OSPF on my channel, it's going to give you a list of close to a dozen videos with more information and specifics regarding OSPF if you want to pursue it further. And here's the great news about OSPF is that once we have a plan in place about what we're going to do, the actual implementation is really just a few commands. And I guess one little wrinkle in that scenario is that there's a couple of different options. In fact, there's 3 or 4 different ways of enabling these networks to be part of OSPF. So for example, here on R1, we could go into the router configuration and use a network statement to include 10.1.0 and 10.12.0, or we could go into those individual interfaces and say interface by interface, hey, you're included in OSPF and specifically in OSPF Area 0. And so the method I'm going to demonstrate in this video as far as implementing OSPF is I'm going to use router configuration mode. And so when I say router config, I'm not talking about just generally configuring, the router as a whole, but the specific OSPF routing process is where I'm going to specify things such as the process ID. And in router configuration mode for OSPF, that's where we can use a network statement to indicate that, hey, any interfaces, Mr. R1, that begin with 10, go ahead and include those interfaces and those directly connected networks as part of OSPF. And as part of the network statement, we're also going to specify which area those matching networks belong to. So we're going to use area 0 across the board, and we'll use a network statement that brings in any interfaces that begin with an IP address of 10. So that's going to bring in 2 interfaces here on R1, it'll bring in 3 interfaces here on R2, and it'll bring in 1 interface here on R3. Also in router configuration mode, that's where we can specify exactly what we want the router ID to be. And then what we would expect to have happen is fully adjacent neighborships between R1 and R2 for OSPF here, and fully adjacent neighborships here between R2 and R3. And that's assuming we don't mess up any of these details that need to match between those devices for them to become neighbors. And then we'll wrap it up with a beautiful little bow by training R3 to advertise a default route into OSPF so that R1 and R2 can dynamically learn via OSPF about a default route. And that would train them on how to forward packets above and beyond the 10.1.0, 10.2.0, 10.12.0, and 10.23 networks. So without further ado, let's go to the CLI and let's enable OSPF. So to save a little bit of time, I've got tabs open to router 1, router 2, and router 3 using secure CRT here. And I've also configured this command window to send the commands I type here down at the bottom to send it to all 3 routers simultaneously. So on all 3 routers, I'm going to go into configuration mode with configure space terminal. And just to confirm, I'm going to tab across. Oh, I need to update that. Send commands to all sessions. All right, let's go ahead and try that again. Config T for config terminal. And let me tab across. And sure enough, we are now in configuration mode on all 3 routers. And then I'm going to specify router, OSPF, and I'm going to specify the process ID number of 1. So effectively, this is training each router that it should run OSPF, and locally, it should identify that routing process as process ID 1. In the event we ever need to run like a second or a third or a fourth instance of OSPF. And in very small networks, it's extremely rare that we would ever need to run more than just one OSPF routing process. I mean, really, how many do we need? So here on each router, I'm going to configure a router ID. So on router 1, it's going to be router-ID, and it's going to be 1.1.1.1. And on router 2, in the OSPF configuration, it's going to be router ID 2.2.2.2. And on router 3, based on our plan, it's going to have the unique identifier of router ID 3.3.3.3. That is if I could type. All right, there we go. So now we have router OSPF 1 on each of these routers. We've also specified the router ID for router 1, router 2, and router 3. Next, we're going to go ahead and train each of the routers that any interface that begins with 10 as far as the IPv4 address, that should be included, that directly connected network and that interface should be included as part of OSPF. So to do that, we're going to use a network statement. So I'm going to say network 10. Then I'm going to use a wildcard mask to indicate we don't care about the second, third, or fourth octet for matching. Effectively, this says any interface that begins with 10, boom, you are in OSPF. We also need to specify which area those interfaces are going to belong to in OSPF. So we're using OSPF area 0 for all the networks that begin with 10, and we'll press enter. And that's it. So we type in end, and I'm doing that across the board. And let's do a show IP protocols. And show IP protocols is going to show us our dynamic routing protocols that we have running on a Cisco router. So here on R1, we have OSPF running with process ID number 1. The router ID for router 1 is 1.1.1.1. And here is our network statement of 10.0.0.0 with a wildcard mask that says we don't care about matching on anything in the second, third, or fourth octet. And any interfaces that do begin with a 10, as far as the IPv4 address, they are also going to be included as part of area 0, based on our topology and our plan. Also, we can see right here on R1, we got a message saying, hey, we have an adjacency. And that adjacency is between R1 itself and the device that has a router ID of 2222, which is R2. So if we went over to R2, we'd have similar information. We're running OSPF process ID 1 locally on R2. Its router ID is 2222. It has a network statement saying any interfaces that begin with 10 should be part of OSPF and included in area 0. And it has 2 neighbors that came up. It has a neighbor at 1111, which is R1, and it has a neighbor at 3333, which is R3. And one way of verifying that is with the command show IP OSPF neighbor and pressing enter. So here R2 is saying, yep, I've got a full adjacency with the neighbor 3333. That's R3's router ID. And I've got a full adjacency with the neighbor ID at 1111, which is R1's router ID. So here in R2, if we do a show IP route, it's going to show us all the routes that this router knows about. So this router is directly connected to the 10.2.0 network. That's where PC2 is. This router is directly connected to the 10.12.0 network, which is the network between R1 and R2. It's also directly connected to the 10.23 network, and that's this network between R2 and R3. It also knows about the 10.1.0 network that it learned via OSPF. And this is one of those situations where administrative distance kicks in because R2 knows about the 10.12.0 network and the 10.23 network because it's directly connected, but those networks are also being advertised in OSPF. So why are they showing up as directly connected routes rather than OSPF routes? And the answer is administrative distance. For a directly connected network, the administrative distance is 0 for a directly connected network. For OSPF, for example, right here, the administrative distance is 110. And so if you have to choose between an AD of 0 and an AD of 110, you're going to use the AD of 0. And that's why we have these directly connected networks showing up on R2 for this network, and this network. And for the 10.1.0 network, which R2 is not directly connected to, the best option regarding that route was learned via OSPF. So that's why this route that's in the routing table for 10.1.0 has an O in front of it. It was learned via OSPF. And there's the administrative distance for OSPF of 110. And there is the cost of that route in OSPF. So each of these routers has full access to the 10 networks. So here in R1, if we do a show IP route, or more specifically, we said show IP route for OSPF learned routes, it has learned about the 10.2.0 network and the 10.23.0 network. So R1 knows how to reach all the 10 networks shown in this topology, but what it doesn't know how to reach is anything out on the internet. And so if we take a look at router 3, and it does have a default route, we'll do a show IP route. It has a default route. So if we want to train R3 to advertise the default route into OSPF, we're going to use this command. We're going to go into router configuration mode for OSPF, and we were using process ID 1, so we're going to go back into that same exact routing process. And here in router OSPF configuration mode, we're going to say default information, originate, and press enter. And what that says to R3 is that if I have a default route, says R3, I'm going to inject that or advertise that default route into OSPF. So at the end of the day, R1 is going to have a default route that forwards towards R2, and R2 is going to have a default route that forwards towards R3, so that both R1 and R2 have a default route learned via OSPF. So we can verify that by going back to R1, and here on R1, my hands will never leave my arms. We'll hit the up arrow key, do a show IP route. So now we have this OSPF learned default route that says, hey, if you need to forward and you don't have a more specific route in your routing table, your next hop is going to be 10.12.0.2. And if we looked at R2 and we did the same thing, hit the up arrow key for show IP route, R2 also has a default route that says, hey, if I need to forward traffic and I don't have a better match in my routing table, go ahead and forward the packet to the next hop of 10.23.0.3, which is R3. And on R3, if it gets a packet, I'll go ahead and do a show IP route here as well. If R3 gets a packet and it doesn't have a better match in its routing table, it also is going to use a default route with the next top router at 192.168.1.1. So to verify that it all works, let's go over here to this PC1. And here on PC1, it did the DHCP discover offer request acknowledgement sequence. It's got the IP address of 10.1.0.100. It's using a default gateway of 10.1.0.1. That's R1. And let's do a ping out to www.cisco.com. And it resolved that using DNS. It resolved that to an IP address. And it sent out 5 pings. We can also do a trace here on this little virtual PC to verify that as well. So we type in trace, and then we go to www.cisco.com once again. It should do name resolution again, and then it's showing us each of the hops in the path as it goes out to the internet. So the first hop was its default gateway at R1. The next hop was R2, then R3, then a few other devices in my home, and then off to my service provider, and then finally another router just prior to hitting the destination IP address, who then responded back to us. So thanks for joining me in this tutorial for OSPF. And if you want hours and hours more content regarding OSPF, it's sitting there waiting for you on my YouTube channel. Just go to my channel and do a search on my channel for OSPF, and boom, that list will be provided. Until then, happy studies, have fun, and be nice to everybody. I'll catch you next time.
What you're putting in, all your hopes and efforts are all in